Welcome all. So, today we will continue the lecture on blast loading and its effects. So, last time we were seeing the free airburst explosions. So, we have seen the effect of the free airburst explosions, and now we will talk about the signature that is associated with the free burst explosion. So, last time we saw the scale distance and the blast parameters. So, we established that parameter called the scale distance has been made, where what it tries to do is that it tries to establish the equivalency of the blast pressure in terms of the standoff distance and the weight of the charge. And these parameters, peak pressure, impulses, durations, can be used for the design of the protective structures. And from here we can construct the design charts. So, as we have seen earlier, here if you look very closely here, if we enlarge this section, there will be a steep increase in the pressure profile. So, this is the incident pressure, this first line, the green line is the incident pressure, and depending upon the configuration of the structure and the location of the blast load, there can be a significant increase in the amount of the pressure, and this is called the reflected pressure. So, the reflected pressure can be significantly greater than the incident pressure. And this is measured normally from the ambient pressure. And so, this is called the positive phase duration, and after that it goes into the suction phase or the negative phase, and this is called the negative phase. So, in the negative phase, pressure will be either reflected pressure or the incident pressure, both are less than the positive phase duration, but the negative phase is significantly larger than the positive phase duration. And positive phase and the negative phase duration together are known as the total duration. So, moving ahead. So, here we are talking about the charts. So, here we can see different types of charts. So, in the x axis we have the peak incident pressure, and on the y axis we have a normalized reflected pressure. This is being normalized with the peak incident pressure. So, here we can see, depending upon the signatures, the peak incident pressure, the relationship between the peak incident pressure and the reflected pressure. So, here we can see the reflected pressure can be significantly larger than the incident pressure. And depending upon the scale distance, different parameters like reflected pressures, incident pressures, positive impulse, negative impulse, reflected impulse, time positive, time negative, all this can be calculated. So, let us say we have a structure, and we know the weight, we know the scale distance r. So, from here we can construct our z parameter, that is the scale distance, r cubic of this w, and putting this thing in the x axis, I can calculate all the required values. I can calculate the reflected value, I can calculate the incident value, time positive time period, negative time period, impulse, and all those things. So, these are the empirical charts. So, the beauty of this empirical charts is that we need not go into the specific calculations, we need not go into the messy design charts and all those things, but here we can have a very good estimate about the quantities. The only drawback, I will not say drawback, the only issue with this type of charts is that they are constructed based on an envelope of different experiments. And if you are taking an envelope, what we normally try to do is that we try to overestimate these quantities. Why it is overestimated? This is a load parameter. So, load parameter, if it is overestimated on the upper hand side, then the loading value will be more. So, then the design of the structure will be more over conservative. So, though these values are easy to use, okay, but they are normally overestimated. Okay. So, these design charts can be very easily used for the estimation of the different quantities like reflected pressure, incident pressure, impulses and other quantities. Okay. Only thing is that we have to know the scale distance, okay, that is the weight of the charge and the standoff distance. Okay. Now, we come to the airburst explosion. Okay. So, an airburst occurs when a detonation takes place above the ground and at a distance from the protective structure. Okay. So, in the free air burst, what was happening? In the free air burst, the burst was happening above the structure. Okay. It was above the structure, adjacent to it, but it was above the structure. Okay. In an airburst explosion, the detonation takes place close to the ground. Okay. There is a small distance between the explosion and the ground. Okay. The blast wave propagates outwards, striking the ground before reaching the structure. Okay. In the free air burst, the blast wave was propagating spherically. Okay. It was propagating spherically and it was hitting the structure. Okay. In air burst, the blast wave propagates outwards, striking the ground before reaching the surface. Okay. So, it starts propagating, okay. It will strike the ground before it reaches the surface. Okay. The interaction of the incident blast wave and its reflection of the ground form a reinforced pressure front known as the Mach front. Okay. So, there will be an interaction, okay, between the reflections from the ground, the reflected pressure from the ground and the incident pressures. Okay. And where it is reflecting, it will create a this type of front. Okay. So, this is known as the typical triple point. Okay. So, these are the incident waves, okay, incident waves, okay, and then there were reflected waves from the ground. Okay. Again we can see that. So, incident waves, okay, when it hits the ground, they will form the reflected wave, okay, and their interacting point is called a path of a triple point. Okay. So, the interaction of the incident blast wave and its reflection off the ground forms a reinforced pressure front known as the Mach front. Okay. So, there will be an augmentation of the pressure and this will form what is known as a Mach front. Okay. The Mach front can be approximated as a plane wave for design, as the pressure variation along its height is minor for practical purposes. Okay. So, it will form a plane wave. Okay. So, it will act as a, so from here it will act as a plane wave, okay, and this will hit the structure. Okay. So, this typical thing is different from the free air burst. Okay. So, due to the reflections from the ground, there is an interaction and this path is known as the triple point and a planar wave is formed, okay, which hits the structure. Okay. So, Mach front and the triple point. Okay. The Mach front height increases as the wave propagates outward, tracing the path of the triple point where the incident wave, reflected wave and the Mach front intersects. Okay. So, here we can see, okay, from the point of the interaction of the incident wave and the reflected wave, this front is formed. Okay. So, this is called the path of the triple point. Okay. And this height depends upon the path of the triple point. Okay. So, the Mach front height increases as the wave propagates outward, tracing the path of the triple point where the incident wave, the reflected wave and the Mach front intersects. Okay. When the Mach front or the triple point height exceeds the building height, the structure experiences uniform blast pressure. Okay. So, here, okay, here in this case we can see that the structure is like this only, okay, and the height of the triple point, okay, is more than the height of the structure. Okay. So, what the structure is seeing is a uniform pressure. Okay. Let us say the structure was like this, okay. Then only till here it will see a uniform pressure. Okay. So, if the height of the MAC front, okay, or the height of the triple point is less than the height of the structure, then the entire structure will see on what is known as the planar wave only. Okay. So, the structure will experience the uniform blast pressure. Okay. If the triple point height is below the structure's height, the pressure at the structure varies with the height. Okay. The same thing that we were telling. So, this is the pressure time variation for the air burst. Okay. So, this is the MAC or the incident pressure. Okay. Okay. So, the blast pressure variation with height. Okay. So, what happens to the variation of the blast pressure as the height increases. Okay. So, the below the triple point, okay, the pressure history on the structure is influenced by combined effect of the incident and the reflected pressures. Okay. The pressure time profile differs from that of a pure MAC front. Okay. The pressure tends to be lower above the triple point. Okay. Since above the triple point the interaction is not there, so the pressure is inherently below the triple point. Okay. Most buildings are far enough from the detonation that the MAC front fully envelops them. Okay. However, this variation can affect taller multi-story structures. Okay. If the explosion is occurring significantly far than the structure, okay, then what will form is that till the structure reaches, okay, there will be an interaction from the incident and the reflected pressures, okay, and the MAC front will be higher than the structure itself. Okay. But if the building is significantly higher, then the variation of the blast load will occur. Okay. Since the entire structure is not engulfed by the pressure loading. Okay. So, this is the effect of the scaled horizontal distance from charge, okay, and this is the scaled height of the triple point. Okay. Invariably what is being told here is that this is the variation of the z, okay, this is the variation of the z and this is the variation of the triple point. Okay. So, this is the scaled variation of the triple point, okay, with respect to the blast charge. Okay. So, as we can see, as the scale distances increases, okay, the height of the triple point also increases. Okay. It means that the structure is significantly at a distance from the blast effect. Okay. And this numbers, okay, these numbers they are indicating scaled charge heights. Okay. So, the calculation of the incident peak pressure and impulses. Okay. So, depending upon the angle of incident, okay, so you can see that as the angle of incident is increasing, the pressure, the incident pressure and the impulse is decreasing. Okay. So, it is but obvious. Okay. So, this is the angle of incidence, okay, alpha. Okay. So, as the angle of incidence increases, the value of the pressure decreases. Okay. So, to determine the air blast load on a building surface, we first evaluate the peak incident pressure. Okay. First the peak incident pressure is evaluated and impulse at the site on the ground just before the structure. Okay. So, first the peak incident pressure is being evaluated. Peak incident pressure is obtained using the scaled charge height and the angle of incidence from this figure. Okay. So, using this figure we can obtain the peak incident pressure. Okay. So, using the same parameter we can determine the impulse also. Okay. Using the same logic we can determine the impulse. Okay. Now, these values correspond to the peak overpressure and the momentum delivered by the blast wave at the point of intersect of the ground. Okay. So, we have calculated the peak overpressure and from the impulse we get an idea of the momentum also. Okay. That is a resultant of the blast interaction. So, once we have calculated the peak incident pressure and the impulse, okay, other blast parameters can be easily estimated by equating this to peak incident pressure. Okay. And its impulse from the MAC wave. Okay. The scale distance corresponds to PSO is found from the figure 7. Okay. So, using the below charts, okay, we can calculate the all the blast parameters. Okay. The scale distances allow the derivation of the parameters including. So, using the scale distances we can calculate the reflected pressure, refraction pressure, shock velocity, positive and negative pulse wave length and the positive and negative phase durations. Okay. So, since we can calculate these two quantities, okay, from these two quantities we can derive easily the other quantities as well. Okay. And after that these values are adjusted by multiplying with the TNT equivalent design weight for final calculations. Okay. After that the TNT equivalent term is being multiplied in order to get the actual number. Okay. Okay. After that we are talking about the surface burst explosion. Okay. So, now we are talking one by one in the unconfined blast. Okay. We are dealing with the unconfined blast. Okay. We looked into the free air blast. In the free air blast, the blast occurs above the structure and it follows a spherical path. Okay. In the air blast, the blast occurs above the ground. Okay. And its signature is a mixture of the incident waves and the reflected waves. Okay. There a Mach front is being made and using the available design charts we can calculate the different quantities, the overpressure, the reflected pressure, the incident pressure, impulse, positive phase duration, negative phase duration and all the required quantities. Okay. Now, we are dealing with the surface burst. Okay. So, let us see what happens in a surface burst. So, in a surface burst case, the charge normally detonates very close to the ground. Okay. In an air burst, the charge was detonating at a finite distance from the ground. Okay. Here the charge is detonating very close to the ground. Okay. So, the initial wave interaction. So, the incident shock wave reflects off the ground surface immediately, merging with the incident wave to form a single hemispherical wave. Okay. So, earlier what we have seen, if it is located at finite distance, so there will be an incident wave and then will be a reflected wave. Okay. And this will form a Mach front. Okay. But here what will happen is that the incident shock wave will reflect off the ground immediately. Okay. So, the reflection will occur immediately. Okay. So, there is not much distinction between the reflected wave from the ground and the incident wave. Okay. And this will merge immediately with the incident wave to form a spherical wave front. Okay. So, now the spherical wave front will be formed. Okay. And this is the assumed planar wave front. Okay. So, the wave shape, this combined wave front behaves similarly to Mach wave, but it is hemispherical due to the ground interactions. Okay. So, this is similar to the earlier thing, but earlier there was a distinct planar wave, but now a hemispherical sort of wave will be formed. Okay. So, and a part of it is assumed as a planar wave front. Okay. Significance. Okay. The blast loading from surface burst is generally larger than the free air burst at equivalent charge weights and distances. Okay. So, this effect, okay, from the surface burst is generally larger than the free air burst at equivalent charge and weight and distances. Okay. So, if we keep the parameter r, okay, equivalent charge wave w and the standoff distance same. So, in this case, okay, the surface burst will have more significant effect than the free air burst. Okay. Okay. So, blast parameters. Okay. Similarly, as in the case of air burst, so using the same principles, okay, and the same established equations, we can calculate the different parameters associated with the blast loading. So, we will use the same parameter, that is the scale distance z, which is made up of standoff distance and the equivalent TNT. So, using this scale distances, okay, if we take any number, okay, for example, here we are taking the distance r, and if we are taking w, okay, so we can calculate our z, okay, r cubic root of w, okay, the standoff distance and the equivalent charge. Okay. So, using these two numbers, okay, we can get our x axis, and from the x axis we will get all the required quantities from the y axis. Okay. The reflected pressure, the incident pressure, impulse positive, impulse negative, time period positive, time period negative. Okay. So, we can calculate all the required quantities, okay, using this empirical charts. Okay. So, the use of this empirical chart is very handy. Okay. At one go we can calculate all the required quantities, and this type of charts are readily available in different types of manuals like TM 5 1300, UFC 3 34002, which is being shown out here. Okay. So, we can use any of these charts to calculate the required quantities. Okay. So, going ahead in the surface burst explosion. So, here for a surface burst we are using a hemispherical TNT. Okay. What does it means? It means that we are using, this burst is hemispherical in nature. Okay. So, this shape and the charge we have taken into account in terms of W. Okay. That is the equivalent TNT. Okay. So, we have established the shape and the charge effect in terms of the equivalent amount of TNT. Okay. So, blast parameters depending upon the TNT. Okay. So, again using different charts, okay, we can calculate the positive phase parameters, negative phase parameters, and all the associated parameters that we require. Okay. So, again PS, PR, okay, I positive, I reflective, okay, I incident, I reflective, time period negative, okay, blast length negative, okay. All the parameters that we require we can calculate using the design charts. Okay. Okay. So, all these parameters exceed the free air burst value for same charge and the scale distances. Okay. So, if we compare all these quantities, okay, so if we compare free air burst, okay, with the surface burst, okay, all these quantities in the surface burst explosion will be greater than the free air burst quantities. Okay. So, again similarly these quantities can be used for evaluating blast load on the structures subjected to the surface burst. Okay. So, similarly whatever in the similar way in which we have used the free air burst quantities, we have used the air burst quantities, we can use the surface burst quantities also to design for the blast loading. Okay. And again it overestimates the parameters. Okay. So, we will always have a overestimated design on the right hand side. Okay. So, our design will be safer, okay, or it will have a more reliability. So, blast load assessment for surface burst. So, calculation method. So, we will treat the surface burst loading similar to air burst method, but use surface burst specific charts. Okay. So, here the key thing is that the charts that we are using. Okay. So, if you look into all the charts, okay, if you look into all the charts, okay. So, here it is not specifically written, but there most of the times it will be written that this is for the air burst case. Okay. So, we have to be careful, okay, about the charts that we are using. Okay. So, this will be for the air burst chart. Okay. So, whenever you are estimating the quantities, we have to be careful that we are using the appropriate charts. Okay. Okay. So, here we can see that it is written that this is for a hemispherical TNT for the surface burst. Okay. And the pressure is also maintained. Okay. This is occurring at the sea level. Okay. Again hemispherical TNT explosion at the sea level. Okay. So, the pressure conditions and that type of burst is mentioned here in all the charts. Okay. So, we will have to be careful that we are using the appropriate chart. Okay. So, normally the parameters are tabulated up to a scale distance of z equals to 100 feet per cubic pound. Okay. So, normally you will see that this goes till a value of 100. Okay. Okay. This is again for a value of 100, approximately 100. Okay. So, these charts are normally made for a value of z equals to 100. Okay. For non-TNT explosives, if the explosives is from a non-TNT. Okay. So, we will use the scaled peak pressure and impulses for actual explosives adjusted by a 20% safety factor on the weight. Okay. So, we will convert them to an equivalency, and then we will have a range of 20% to take the safety margin. Okay. Because the non-TNT explosives, okay, do not behave in a more controlled manner as an TNT explosives. Okay. So, a 20% of safety margin is kept in the design process. Okay. So, the normally input parameters are peak incident pressures and the impulse. Okay. That is read directly from the chart. Okay. We obtain these quantities directly from the chart, and the corresponding reflected pressure and time pressure are obtained accordingly. Okay. Okay. So, in this particular chart everything is mentioned together. So, if we take any point, okay, we will get the equivalent quantities. Okay. We will get the reflected pressure, we will get the incident pressures and the time and length and all the associated parameters. Okay. We will have to be careful that we are taking for the, we are accounting for the proper graph, that is if we are dealing with the free air burst, we are using the graph for the free air burst, or if we are dealing from the surface burst, we are using the surface burst charts. Okay. If we are using a non-TNT explosives, then after converting from for the TNT equivalency, we will have to adjust by a 20% safety factor. Okay. Because the behavior of the non-TNT explosives is not as repetitive as the, or not as reliable as the TNT explosives. Okay. So, we will have to account for the, you have to account for at least 20% for the safety margin. Okay. And we calculate the peak overpressure and the impulse, and then we go ahead with our design process. Okay. What happens when multiple explosion occurs? Okay. So, the definition. So, the multiple explosion occurs when two or more explosive charges, typically of similar materials, detonate several millisecond apart. Okay. It means that there will be an array of explosives, okay, and it will be a chain type of event. Okay. So, one explosion occurs within some milliseconds, it propagates, and the second explosion occurs, and other explosion keeps on occurring. Okay. So, normally all these are made up of similar material. Okay. So, if it is one is made of TNT, other will also be made up of TNT. Okay. So, the wave propagation. So, the blast wave from the initial detonation travels ahead of the waves from the subsequent explosions. Okay. This wave will travel first after this blast occurs. So, this wave will be behind the waves from the first explosion. Okay. The phasing, timing and direction of the subsequent blast wave depends upon the initial times and the spatial orientation of the explosives. Okay. So, how these explosives are oriented one with respect to another, okay, that will determine the blast wave propagation and the time of the detonation. Okay. So, wave interaction, if the time delay between detonation is sufficiently small, the blast wave from subsequent explosions will merge with that of the initial explosion. Okay. If these things are kept very close, okay, then what will happen is that there will be really very less distinction between the different blast waves, and they will all act as a single blast wave formation. Okay. So, the blast wave from the subsequent explosion will merge with that of the initial explosion. Okay. It means that they will act more or less in unison. Okay. So, the factor affecting the merger distance, magnitude of each explosion, let us say the first one is very large, okay, its weight is 100 W and the other one is maybe 0.1 W. Okay. So, the first one will detonate and this will act as a signature of the first blast also. Okay. Time delay between the explosions, okay, if the time, okay, or if they are kept very at a very small distance, okay, and the time of detonation is very less between the two, okay, then this will be all will be merging and then they will act in unison. Okay. Spatial separation and explosions and orientation of the explosives. Okay. So, the blast waves, okay, will try to add up if they are kept in a similar orientation. Okay. Presence of obstruction, if there is a obstruction like buildings, walls, terrains, okay, if the obstruction is much, okay, then there will be a delay between the explosions, okay, and if there is no obstructions, okay, then they will try to act as a single blast loading. Okay. So, depending upon the obstructions, there may be distortion or obstructions of the blast wave propagation. Okay. So, with the multiple explosions, we will stop here and we will continue from the next time. Thank you.